Alright guys, in this video about similar figures, we're going to talk about the triangle midsegment theorem. First, we're going to explore what the triangle midsegment theorem is, and then I'm going to do 4 examples. So let's get started. Okay, so the definition of the triangle midsegment theorem states when a line segment is the midpoint of two sides of a triangle, that segment is parallel to the third side and is half its length. So watch what happens here. If I take this triangle and I drag it over and place it on top of this triangle, I am creating a situation similar to the proportional triangle theorem. But in this case, we have created a special scenario where this point here is the midpoint of these lines. And in doing so, this line here is half of that line. I really like this theorem because I've used it personally when constructing a roof for my shed, and it helped me create some attic space up there, some top storage. It's a pretty cool little theorem that used to be used a lot and isn't really used too often in modern houses, but helps create like attic space and all that other stuff. And if you really look around at frames that involve triangles, you kind of see it in there, that in the proportional triangle theorem. So a big point I'm trying to take home here is that these are structural theorems. They don't really get talked about in this kind of light anymore, but I believe it's how the ancients went about things. So let's take a look at a few examples. Okay, I have not spoken about an equation, and I kind of waited to get to this problem to do that. Oftentimes, the triangle midsegment theorem is kind of listed or presented something, let's say, like this. And I really don't care for that. Here is the reason why. The reason is because it does not look like a proportion. So another way we can do this, and I'm going to use this simple example, is to create a proportion. The scale factor between these two triangles here is 1/2. I know that because E and D are the midpoints of the segments ZY and XY. I know that because of these congruency marks here. These are indicating that those points are in the middle. So, in essence, we kind of look like we're making up rules when I write something like that. Or I write something like this. This is yet another proportion. These are still similar triangles because there's a scale factor between them. So I like to use the scale factor. And the way I do this is 1/2, and this is the large side and this is the small side. Or big triangle over small triangle equals big triangle over small triangle. So I think I've written something like this before in my videos. It's been a while since I made a similarity video, and I'm kind of still applying that. Now what I'm going to do is cross multiply and solve. I am choosing this example here to present my world dominating plan to convert the way we look at triangle midsegments as a proportion because it's a very straightforward one. So x equals 9, which is exactly what the theorem states, right? This is exactly half the length. So ED is exactly half the length of ZX. So if you're asking why is it that I went through all this trouble if we already know what the theorem is, my response is, yeah, you didn't have to do any of this. You could have just recognized that ED is half of ZX and labeled it 9 and moved on. But that wouldn't help us in the next examples. So let's take a look. Okay, so this is a commonly asked standardized test question here. And it says the triangle below DEF are the midpoints of the sides. What is the perimeter of triangle ABC? So let's get started. Remember, the theorem states that the line that is the midpoint is half the line it is parallel to. So EF is half of AC, which is 12. DF is half of CB, so that's 14. Then DE is half of AB, which is 16. And now I add those colors. I add those numbers together. And the reason why I do that is because you find the perimeter by adding up the side lengths of the shapes, the outside side lengths. Coincidentally, let's take a look at something. So if I were to write 6, 8, let me actually put the 7 here. 7 and 8, and added those together, I would get 21. Notice how the scale factor, which is often represented as K, is 1/2. That's how proportionality works. The scale factor exists throughout. I've talked about this in great length. Alright, let's take a look at the next problem. This is another problem that's commonly asked. We put algebraic expressions into these geometric concepts, I guess, to attempt to make things analytical. I don't know. But be careful and don't let this take away from the concept of proportions. Now, I know that W is the midpoint of ML. I know that because of these congruency marks. So what that means is I don't need this because V is also the midpoint of MN. So I do not need this. And now what I could do is I could set up a proportion using the scale factor of 1/2 because I have recognized that I have a triangle that is built using the triangle mid-segment theorem. The small triangle goes on top, so that's 2x minus 11, and the large triangle goes on the bottom. Be careful when you do this. A lot of students flip these things. That's one issue. The other issue, students are trying to judge the lengths of the sides by the expression. Judge the lengths of the sides physically. So this WV is definitely shorter than LN. It physically looks that way. And in geometry, while we can't necessarily say we know the scale, we could say that we physically acknowledge that WV is shorter than LN. At some point you've been taught, don't count shapes, the shapes aren't made to scale. That part's true. But, right, so but, WV is shorter than LN, and we could take that from the picture. So that general concept. So now what I'm going to do is I am going to cross multiply and solve. And part of the reason why I like solving this way so much is because if you have been working on proportional parts before, this is all a similar process. No pun intended. So, in other words, you have been doing this very same thing in solving your similar figures the entire time. The only new thing is to recognize is that you have a scale factor of 1/2, and you have to use that to set the proportions. I have brought this up before. I like to keep my x term positive whenever possible, so I am moving my 2x over the equal sign and subtracting that, creating 0 on the one side, and then bringing this down here. And now I'm going to add the 22 to both sides, creating the 0 here. So that's 2x equals 16. And now I need a 2, that 2 to become a 1. So I'm going to divide. So I could have 1x here. I'm going to divide on both sides. So I get x equals 8. And that is my answer. Okay, let's check something out before I close out this video. Okay, I went and plugged that 8 into all the variables. So what I have going on here now is I have this length here is 18, and that means this has to be 9. This length here is 20, that means this has to be 10. This length here, WB, is 5, and LN is 10. If you look, the proportion is going to stand throughout. So I can now start setting these up however I like. So I could set this up 10 over 20. So 10 over 20 equals, let's say, x over 18. And when I cross multiply this, I will end up with 9. And that will happen throughout the shape now. Again, I just wanted to take a second and quickly illustrate how this is a proportional theorem. It is often not displayed as one. It looks like the rules are changing, and that's not the case. And when you solve using this proportion, you are finding, potentially, you can find the shapes or the sides to the entire triangle, depending on what you have. Okay, guys, I hope you have found this video to be helpful.